Ladies and gentlemen, here we are, last new material. And really, guys, again, it's just a continuation of the last stuff. Alright, it really is. The big difference here is right here. We need to use identities, and we need to be able to use factoring. Alright? So right here in the hint, it tells us angles must match. Trig functions must match. That means, like, if I'm seeing 2 theta, I need to see 2 theta everywhere. Alright? Or theta everywhere. You can't change that. The other idea is that our trig functions must match. So we need to be using all cosines, or all sines, or at least to a place where we can factor them apart. To use our favorite zero product property. Zero product property. I don't know why I did it down like that. I'm just wasting time. Okay, zero product property. Alright? So let's get into it. For example, right here, when I look at something like number 1, well, I can't just I don't know. I don't just have cosine 2x equals 0. I can't really move this over. That's not really going to help me. It doesn't get me a ratio. So what we're going to have to do here, guys, is we're going to have to recognize that if I have a cosine 2x in both places, well, then I can do a little bit of factoring. And this will be nice, because then when I factor out that cosine 2x, I'm left with 2 sine 2x plus 1 equals 0. And this is what I'm looking for, guys. This is what I want, because now, just like what we did back in chapter 2, I can now use the zero product property, and I can say, well, the cosine of 2x has to equal 0, and 2 sine 2x plus 1 must equal 0. So if I keep going on this, I think it's going to be 2 sine 2x equals -1, or sine 2x equals -1/2. Alright, and this is great because I can now use the same tricks that I've been doing for the rest of this chapter, right? I can use my unit circle here, I can use my unit circle here. So let's do it. So I want to sketch a unit circle. Cosine 2x equals 0. Well, that's in 2 places. My x value is 0, straight up at pi over 2. It's also down here at 3 pi over 2. Let's see. I also know that I have sine has to be -1/2. Well, that's here at, what is this, 4 pi over, oh no, what am I saying? No. Sorry about that, guys. 7 pi over 6, or over here at 11 pi over 6. Alright, now when we look at this, I would say I'm going to need 3 equations here. I'm going to need 3 equations. I know that because it's taking me, let's see here. Oh, you know what? I'm going to actually think about it like this. I'm going to say, well, this first one, from pi over 2 to 3 pi over 2, I can write one equation for these two, right there. So let's do that first. That's going to be 2 theta equals pi over 2 plus or minus pi n. And then, let's see here. Oh, I need 2 separate equations for the 7 pi over 6 and the 11 pi over 6, because I just need to go here and then all the way back around and around and around. Okay, so another 2 theta equals 7 pi over 6 plus or minus 2 pi n. And 2 theta equals 11 pi over 6 plus or minus 2 pi n. So let me try to number these so you understand what I'm getting these from. I am getting my first equation, this one over here, because of 1 and 1 All right, these both go to this equation. Now my next solution goes to this equation, and my last solution goes to my last equation. All right. Now the last thing, I just have to write these in general, but they're in form of 2 theta, and I just want theta. And actually, to be honest, I should have been using x's, shoot. So I'm going to change that now. I'm going to write x. But I know that I have to divide by 2 everywhere. Okay, so when I divide by 2 everywhere, or I guess what Kush wants me to do is multiply by 1/2 the whole thing. Well, then that means I'm going to get x equals pi over 4 plus or minus pi over 2n. Then I need to do the same thing with both of these. Multiply by 1/2, multiply by 1/2, and I end up getting, let's see, x equals 7 pi over 12 plus or minus pi n. And then my last one, x equals 11 pi over 12 plus or minus pi n. And so I have this equation and then these 2 equations as my finals. All right? So again, the big difference here is that I need to do some factoring in order to figure out my 2 equations to get my unit circle. All right, let's try the next one. When I look at something like this, all right, okay, I have a cosine squared 2 theta, I have a cosine 2 theta. All right, so the angles are already matching, but I have cosine squared and cosine. So we can almost think about these as if they were like x's, right? Like x squared and x. So I know that I am going to have to turn this trinomial into binomials multiplied by each other. All right. Well, 2 cosine squared means I'm going to need 2 cosine in one, and then cosine in the other, right? Because when I multiply these back together, I get to 2 cosine squared. If I need it to be minus cosine 2 theta, well, then that means, well, let's see, actually, okay, this is a 1, so I know it has to be 1 and 1. But because it's negative, 1 has to be positive, 1 has to be negative. And hopefully you guys agree that I need this right one to be negative, because when it gets multiplied by 2 cosine 2 theta, that becomes negative 2 cosine 2 theta. And then when I add this one, that's what gets me to my middle piece right there. All right? Because now that we have this, now it's the same thing as before. 2 cosine 2 theta plus 1 equals 0. Cosine 2 theta minus 1 equals 0. And I solve. 0 product property. Okay, so 2 cosine 2 theta equals negative 1. Cosine 2 theta equals 1. I just need to do a little bit more work on this one. Okay, so cosine 2 theta equals negative 1/2. All right? Okay. This looks good. I now have a cosine ratio, 2 cosine ratios actually, so I can plot all of these. So we draw our unit circle, and I start to kind of sketch what I got. All right, so easy one I would say is this one right here. Cosine 2 theta equals 1. That's straight to the right at 0. Cosine 2 theta equals negative 1/2. All right, so that's over here at 2 pi over 3. And last but not least, negative 1/2, I am also over here at 4 pi over 3. Now, this is really interesting. Guys, if you want, you could do this as 3 separate equations, right? Like this, all the way around and back and back and back and back, etc. But I also wouldn't mind you noticing that to get from 0 to 2 pi over 3 is an addition of 2 pi over 3. Well, if we add another 2 pi over 3, we get to 4 pi over 3. And if we add 2 pi over 3 to that, we get to 6 pi over 3, which is the same place. That's 6 pi over 3, or 2 pi. So in this case, we could write this as one equation if we want. All right? So I'm going to write it as one equation. And I'm going to say, well, 2 theta is equal to 0 plus or minus 2 pi over 3n. Just like on the last one, we're going to need to get rid of that 2, so I'm going to multiply absolutely everything by 1/2, which means I then have theta is equal to 0 plus or minus pi over 3n. And your favorite, we make sure, oh, yep, it says for all theta in an interval. All right, so we need to make a list. Well, this list should be nice and easy, right? 0. And then we're just adding pi over 3's. So pi over 3 plus another pi over 3 is 2 pi over 3 plus another pi over 3 is 3 pi over 3, but I'm going to write that as pi plus another pi over 3 is 4 pi over 3 plus another is 5 pi over 3. Now the last one, 6 pi over 3, we have to be really careful. 6 pi over 3 is exactly 2 pi. And if we notice, the interval does not include 2 pi, so we do not include 2 pi or 6 pi over 3. We leave it just like that. All right? Okay, so actually, real quick, before I finish up, let's make sure we write here. This was just a GCF problem. We took out a greatest common factor. Now in the next one, we had a trinomial. All right, so I'm going to write trinomial. We know how to factor trinomials. Last one. Oh boy. 4 terms, a cubic. What do we have for this? I hope you said factor by grouping. I hope I don't run out of space now. Factor by grouping. All right, we're going to need to factor this by grouping. So what do we see here? Well, I know that if I just look at these first two pieces, I can take out a sine squared x. So that's what I'm going to do. I'm going to say sine squared x, and that would leave me with 2 sine x plus 1. And then when I look at my other two pieces, the negative 2 sine x minus 1, what I really want to do, guys, is I just want to take out that negative. So I'm going to do negative 1 times 2 sine x plus 1. And that's going to still equal 0. Well, this is great, because now I have sine squared x minus 1, 2 sine x plus 1, and now I can use some zero product property. All right, so I can say sine squared x minus 1 equals 0, 2 sine x plus 1 equals 0, and I can start solving. All right, so sine squared x equals 1, square root, sine x equals plus or minus 1. Oop, I'm a little off the page there, sorry guys. Still a little off. All right, on this next one, I would just say 2 sine x equals negative 1, or sine x equals negative 1/2. All right, so now the whole idea here, now that we have both of these trigonometric equations, I need to sketch a unit circle. And let's see here. This should actually look pretty similar to number 1. Because I know that my y value is going to be plus or minus 1, straight up, straight down, so pi over 2, 3 pi over 2. And then I know that my y value will be negative 1/2 at 7 pi over 6 and 11 pi over 6. So in the interest of time, guys, what I'm going to do, because I already did this one, is I'm going to just kind of remind you. I'm going to remind you kind of how I did this. When I look at all of these solutions, I know that there is a nice pattern that I can write for these two solutions. This is one equation. But for my others, I kind of need to do them separate. This one and this one. So I would have 3 equations, and I actually already did all of this in number 1. Okay, so I'm going to skip this one or the rest of this one for right now, in the interest of time. All right, okay. So now, that was, and I should go back over this one more time, examples where we factor by grouping, we factor using our trinomial method, and we factor using a GCF. The last page of notes that you are going to need for this chapter is, if I can get this lined up. Okay, so right here. We always need to be on the lookout for identities. That's the hint. We always need to be ready for identities. Let me try to focus this. I feel like it's unfocused. Sorry. Okay. So, in this situation, I don't really know what to do right now. I really don't. Like, I can't just set cosine equal to -1/2 and sine equal to -1/2. That only works when the right side is 0 for the zero product property. So what I could try to do is I could at least try to get rid of this fraction. So maybe I'll do something like this. Like I'll times by 2 times by 2. So now I have 2 sine theta cosine theta equals -1. Okay. Now, obviously, I kind of knew what I was doing. I'm hoping that you guys all recognize this left side. Alright, 2 sine theta cosine theta is an identity. And if you don't know it, well, that's frustrating to me because we've been asking you to write down the identities over and over and over and over and over again. So at this point in time, we should know both left to right and right to left. And this is our sine double angle. So now I can go right to what we've been doing in previous problems. I now have the sine of my angle 2 theta is equal to -1. So I can sketch a unit circle. I know that my y value will only be -1 down here at 3 pi over 2. And I can write an equation. 2 theta, my angle, 2 theta, is equal to 3 pi over 2 plus or minus, oh, it's got to go a full rotation every single time to get to the next solution. All right. So just like we've been doing, multiply everything by 1/2, and I get theta equals 3 pi over 4 plus or minus pi n. It wants all the solutions within 0 and 2 pi, so I have to make a list. Not that bad. Please remember that we can always think about this with a common denominator. So this is just 4 pi over 4. So really here, when I come up with my, I don't even need this, sorry. Just make my list. I have my first angle, 3 pi over 4. I have to add 4 pi over 4, which is 7 pi over 4. If I added another 4 pi over 4, I would get to 11 pi over 4. Oh, that's outside of my interval. So I am done right there. Okay? Cool. Come on. Okay, next problem. Number 5. This is tricky. This is very tricky. I need you guys to remember and kind of be on the lookout for situations like we can't really factor, like if there's not, like there's no GCF here. Well, there is a GCF, shoot. But that doesn't help me with the fact that one side has sines and the other side has cosines. So one thing that I would strongly encourage you to do is to remember the fact that we like to have the same trig functions. And by that I mean I can't really do much with this cosine, but I do have an identity for changing sine squared into cosine squared, and that's what I'm going to do. So I'm going to say I have 3 cosine theta plus 3 equals 2. Now what can I replace sine squared theta with? That's the big deal here. And hopefully we remember the Pythagorean identity that it's 1 minus cosine squared. Alright? Well, now we can get to work. So we have 3 cosine theta plus 3 equals, distribute, so 2 minus 2 cosine squared theta. This is great. This is looking a lot better now. It's not ready, but we're getting there. Now remember, in order, if we have cosine squared and cosine theta, well, we probably need to try to factor this. This looks like it might be a trinomial because it's got second degree, first degree, and then constants. So let's move everything over to one side. So I get 2 cosine squared theta plus 3 cosine theta, and then I have to take away 2, so this is just plus 1, and that's all equal to 0. Oh yeah, this is good. This is nice. Hopefully you guys are seeing that I can now factor this. Right? If I have 2 cosine squared, then I can do 2 cosine theta and a cosine theta over here. And then I just need plus 1s. Right? It's positive 1, so it has to be plus 1, plus 1. And that should make sense, because when you do inners and outers and you add them, you get to that middle term, which is what we needed. So the best part about this is that now I can use the zero product property. 2 cosine theta plus 1 equals 0. Cosine theta plus 1 equals 0. And I just keep solving, right? So let's see here. That's going to be cosine theta equals negative 1/2. I skipped one step, so hopefully you see I subtracted 1 divided by 2. And then I have to subtract here. All right. And now I can sketch a unit circle. Well, cosine theta will be negative 1 straight to the left over here at pi, and cosine will be negative 1/2 at 2 pi over 3, 4 pi over 3, and this is a tough one, guys. This is one where we are going to need 3 equations. We need 3 equations because there's no way for me to get from solution to another solution using a single pattern. All right? So we're going to have to think about this in 3 different ways. We're going to have to think about it as, so what is it? Theta equals 2 pi over 3 plus or minus 2 pi n. Our next solution was pi plus or minus 2 pi n. And lastly, 4 pi over 3 plus or minus 2 pi n. And what's really great is we're done. We are all done with that because we just wanted the general solution. All right, last one. This last one, and actually let me write some notes here. So this one we used the Pythagorean identities. All right, the last one. The last one is tricky because even though we have the same trig function, we don't have the same angle, right? Here's a theta and here's a 2 theta. So we need to try to rewrite one of these pieces in terms of the other. Now, again, I don't have many identities that involve just cosine, but I do have some identities that involve cosine 2 theta. One of them, there's actually 3 of them. If you remember, cosine 2 theta is either cosine squared minus sine squared, all right, or it could be 1 minus 2 sine squared, or it could be 2 cosine squared minus 1. Now, which one do you think is going to help us? If we already have 5 cosine theta over here into 3, yeah, hopefully you said this one, because when I replace it, 2 cosine squared theta minus 1 plus 3 equals 5 cosine theta. Well, this just turns into a factoring problem now. All right, so we got to collect everything on one side. 2 cosine squared theta minus 5 cosine theta plus 2 equals 0. All right, all I did was move that 5 cosine theta over. Let's see if we can factor this. So 2 cosine and cosine, and then we got a 2 here. Ooh, so it's got to be positive 2. So it's either got to be positive, positive, negative, negative, and if we take a look at this middle, we're trying to get to negative 5. Ooh, I think I see it. I need to multiply this 2 by a -2, and I need to multiply this cosine by -1. So that works out, right? -1 times -2 is +2. When I do my outers and my inners, I get to that middle term, -5 cosine theta. So this is great. Sorry, this is equal to 0 still. So let's see here. I can say 2 cosine theta minus 1 equals 0, or cosine theta minus 2 equals 0. Cosine theta equals +1/2. Again, I skipped a step. I added 1 divided by 2. And here I just move over. All right. Unit, circle, time. Let's come over here, draw our unit circle. Well, over here, this is good. Cosine is 1/2. That's at pi/3 and 5 pi/3. Where's my cosine? 2. Where on my unit circle can the x value be 2? Nowhere. There are no solutions for that piece, so you forget about it. Alright, so last thing, we need to see, can we write this? Nope, there's not a single step. So again, I'm going to need 2 equations. I know that my first equation will be pi/3 plus a full rotation. And my other solution will be this 5 pi/3 plus or minus 2 pi n. And it asks for general, so we are done. Alright, so these problems, not the simplest things to do. Things you need to be on the lookout for. Angles must match, trig functions must match, or at least be able to factor apart. Right? I was not able to do anything with this original until I factored out cosine 2x, and then I just had a piece with cosine, a piece with sine, and then I could continue on. Or over here, I didn't know what to do here. My angles were here, I had different trig functions, cosine squared and cosine. I needed to see if I could factor, and I could. So once I was able to factor this, I was able to turn it into what we already know. Same thing on the last one. You didn't even see what I was saying. Hopefully you guys understood what I was saying on this one. Right? Same angle, but different trig functions. So we needed to be able to factor this to turn this into what we already know. Now the last one. Again, if you have 4 terms and one of them's cubic, just like what we were doing in Chapter 2, guys, this is a hint that you need to factor by grouping. So you take whatever you can out of the first 2 pieces, you take whatever you can out of the second 2 pieces, and remember, they should match. This should match. Because once you do that, oh my gosh, then I can solve. Identity page, not the easiest, I get it. But remember, be on the lookout for identities. Know your doubles, know your sums, know your Pythagorean identities, know everything. When I multiplied both sides by 2, this turned into an identity, which is great, because then it was super easy to finish this problem up. Same thing here. You couldn't do anything because you had different trig functions. Well, use your identities to change one of them. Okay? So we changed the sine squared into 1 minus cosine squared, and holy cow, it completely unlocks the problem. As seen here. Right? Change it into cosine squared, completely unlocks the problem. Last one. Identity-wise, please remember, angles have to match, right? Having a theta and having a 2 theta doesn't work. They can't combine unless the angles are the same. So, what do? We use identities to change this cosine double angle into a single angle, which is what we did, and then it factored nicely. Alright? So again, this is the hardest part, probably. It's going to take some work, but it's doable. You just have to practice and be willing to try it. Oh my gosh, please be willing to try. Alright, we will call it there. I know this was a longer video. It's the last new material of the chapter, so yeah, we'll practice some more in class. Later.